Over the years, roller coasters have been depicted by movies and other forms of media as a maniacal machines that injure and kill those who dare to step foot on one. Before we further get into it, make sure to like this video, subscribe to our channel, and hit the bell icon for post notification. Let's discuss the science behind the fearsome roller coaster. Their design utilizes important aspects of mechanical engineering and physics. The first person who depended on design for what could be considered a roller coaster was the 19th century American businessman Lamarcus Adnet Thompson, later known as the father of gravity. While Thompson wasn't the first person to create what we think of today as a roller coaster, he's widely credited for popularizing them. Thompson made a fortune after founding a company that manufactured women's stockings. He was inspired to build his first roller coaster after a trip to the hills in eastern Pennsylvania. There, he experienced the converted railroad line that had become a popular tourist attraction called the Muk Chunk Switchback Railway. This was an 18-mile-long, largely downhill railroad through a striking landscape. It featured a 2,300-foot-long, 665-foot drop at its end and was a huge success with tourists. Thompson wanted to try to capture the essence of the thrill this railroad offered by putting it in a smaller size, and so the concept of roller coaster was born. Thompson named his ride the Switchback Railway, and it officially opened in Coney Island in 1884. It was an immediate, unmitigated success. While modest by the standards of even the most basic roller coaster today, it gave birth to an entirely new type of theme park attraction, loved and feared by millions of people from all around the world. For engineers tasked with designing modern roller coasters, there are several important considerations. The rides must be infallibly safe while also exciting for the riders. This is no small challenge. Most roller coasters tend to consist of four basic components. 1. The train cars must restrain the riders and stay attached to the track. 2. The design of the track. 3. A system to race the car up to the high parts of the course. 4. Some form of brake system to safely slow down the car was required, especially at the end. Roller coasters are commonly made of either steel or wood. For modern roller coasters, steel is usually preferred for its strength and durability. Before they begin, designers work with park owners to figure out what they're trying to accomplish with a ride. They must also determine the course of the tracks and where they'll be placed. For this, designers need to look at the flow of the ride to create rises, falls, and crescendos. This is not as easy as it sounds. Typically, most roller coasters need to fit into a predetermined footprint of land, and so the track design can be pretty involved. Some can also be quite long despite the space restrictions. Roller coasters engineers have also to balance safety needs with keeping the ride thrilling. If it's too fast, it might put off the average rider or make them feel sick. However, if the ride is too slow and sluggish, it'll be boring. Well-designed roller coasters take advantage of the interplay between anticipation and surprise to develop a precisely detailed pace that includes intense thrills followed by lulls. In some ways, this can be considered more of an art form than engineering. After a design is approved, engineers must figure out things like the amount of G-forces that'll be felt by each rider and how much steel is needed. Once the track is designed, the next phase is to make sure it works. One primary consideration is keeping the cars on track. So what is a G-force? G-force is a common unit used by jet pilots, astronauts, and coaster designers. One G-force is the familiar tug of gravity you feel when standing on Earth. This is the force of Earth's gravitational pull on our bodies. Now let's talk about the safety measures they use in a roller coaster. With the complex interplay of forces involved, cars could easily come off the track on corners or hill crests. To ensure this doesn't happen, roller coaster train cars have special safety mechanisms to keep them attached to the track. Early roller coasters relied on wheels similar to those on traditional passenger trains that restricted sideways movements. But as roller coasters became more complex with loop-the-loop and tight turns, more sophisticated solutions were required. To prevent accidents, modern roller coaster cars are incorporated. A series of wheels or a metal bar beneath the track prevents the car from lifting up. Some also have a third set of wheels or bars on the side of the track to ensure the cars will never lose contact with the track. The train cars rely solely on gravity to get them around the track. This requires the strategic placement of peaks in the track design and chain pulley systems to get them there. The pulley system effectively stores up potential energy as it raises the car up a slope. Once at the crest of a peak, the pulley system releases the car and gravity does the rest. These pulley systems often consist of a long length of metal chain beneath the trap and fastened to a loop. This loop tends to be wound around two main gears, one on the crest of the hill and one on the base of it. The bottom gear is usually turned using a basic motor that moves the chain up the hill in a similar fashion to a conveyor belt. Each car of the roller coaster is attached to these pulleys chain using something called chain dogs. These are hinged hooks that hang below the cars and latched onto the chain whenever they come in contact with them. Once the cars reach the crest of a particular hill section, these hooks disengage, and all that stored potential energy is unleashed, much to the rider's excitement or dread. As the car charges around the track, various peaks and troughs either convert the train's momentum into potential energy or release the stored energy into kinetic energy. Most modern coasters consist of several hills. Otherwise, the initial buildup would have to be enough for the car to complete the course. This is a critical part of the roller coaster's design. Engineers also need to consider how the car will be slowed down and stop at the end of the ride. This is accomplished either by designing the tractor passively, which helps reduce the amount of kinetic energy, or by using a system of brakes to slow down and stop the cars. If brakes are required, these are integrated into the tracks. The braking systems tend to be hydraulic, and today, they're also usually controlled by a computer. Roller coasters also tend to have a series of clamps on the track, and at the end of the ride are a fail-safe in case emergency braking is needed. Coasters must undergo much testing before a single person is allowed on. Mechanical downtimes are often evidence that a ride is completely safe. These huge pieces of machinery are designed with the idea of safety first. There are thousands of small things such as hundreds of sensors that detect where a train is, pressure switches that monitor air pressure, solenoids that control the brakes, contractors and drives that control each motor. These are just some of the parts that make rides safe. The roller coaster and ride parts are used hundreds of times a day. Eventually, one of them on one part of the ride will wear out, and if any of one of them does, the ride will go down. All of that is just covering the control system for the ride, but mechanical problems at the ride itself are rare, but it happens too. When the speed of the riders increases or decreases, they experience more or less gravitational force. The modern coaster designs knew that our body can only handle up to 5 g-force, but at some point the coasters reach up to 12 g-force, which is too much for the human body. If the gravitational pressure reaches this extreme, the blood flow to the feet from our brain rises. Thus, it leads to lightheadedness and blackouts when our brain struggles to stay conscious. This is only one problem that affects our body when we ride on a roller coaster. Let's talk about another major problem which can even cause temporary blindness. We had to experience a gradual dimming of our vision after a coaster ride. This feeling is obviously called the grayout. This is caused by the decreased blood flow to the brain and eyes. The eyes fail to react to normal light and our vision gets blurred. This is caused by the positive g-force that we experience on a roller coaster. On the other hand, a negative g-force creates weightlessness, which is also called zero g-force. For a human body, short-term weightlessness is harmless, but that leads to nausea, which is caused by motion causing the suspension of the fluids in the inner ears, and that could cause disagreement of balance. Anyway, the modern coaster designers are properly aware of what our body and the coaster can manage. Coaster engineers design those competing forces in opposition to each other to relieve periods of excessive pressure with intervals of no strain in any aspect. A short transition from negative to positive g-force can result in whiplash, lower back and neck ache. Modern rides are also solidly built to withstand the amount of gravity produced when we ride on a roller coaster. Our body feels 5 times heavier than usual when we're at 5 g-force. For example, if your weight is 100 pounds, the amount of gravitational force applied to your body will be 500 pounds. Engineers must consider the accelerated weight of every single person while designing a coaster. Although these rides are not meant for everybody, many advanced technologies like 3D modeling and simulation software have made roller coasters safer than before and of course thrilling as hell. Now we know almost everything about a roller coaster and its safety. Comment down below any of your crazy roller coaster experiences. Don't forget to subscribe and hit the bell icon.